Hello and welcome to today's Amazon Web Services webcast introducing Amazon Aurora. Before we begin, I would like to walk the audience through a couple items. On your screen, you will see a question pod. Please submit your questions at any time during the webcast, and our Q&A moderators will try to answer them throughout the presentation. We will also address some selected questions in the live Q&A session at the end of the presentation. Today from the product team, as Q&A moderators, we have Lynn Ferrante, Lon Lundgren, and Sailesh Krishnamurthy. Presenting today is David Lang, Senior Product Manager, Amazon Aurora and Amazon RDS for MySQL. Prior to this role, David was the Senior Product Manager for Amazon DynamoDB. Before joining Amazon, David spent 4 years developing and managing at onsite.com. David holds a BS in Symbolic Systems with Artificial Intelligence focus from Stanford and MBA from Duke. Thank you for joining us today, David.
So this is, thanks Colin, it's great to be here. So this is Introduction to Amazon Aurora. To help you guys understand what Aurora is, it would help a lot to understand why we chose to build Aurora the way we did. So when we started off thinking about how to build this service, looking at the way databases were set up in the market, we found that current DB architectures were pretty monolithic. I mean, you had multiple layers of functionality all in a single box. Your SQL, your transactions, your caching, your logging was all being handled by a single machine. And if you needed to grow your database, you have a particularly successful app, your workload is going up. I mean, you had a bunch of options. I mean, one, the standard one is you buy a bigger box. That'll work, but that's also expensive. It's not as cost effective as scaling out. There are lots of issues with that. Another option for you is sharding, which I'm sure that a lot of the people on this call are very familiar with. So with sharding, you connect the shards at the application level. And this can be a pretty good scale-out solution. I've done it. A lot of you guys have done it. But it does have a cost in that you lose a lot of the advantages that you would have with a relational database management system. When you're doing sharding, transactions are hard. You have to worry about concurrency. You have to worry about what's happening when you have a lot of different requests that are all going to your different shards and how they might interact with each other. So that's a problem you have to solve at the application level. SQL doesn't work as well. I mean, SQL, ideally lets you express what you're trying to do and not worry about how it's actually being implemented on the back end. But with a sharded system, the application actually has to be aware of the shards and understand how to run a query across a sharded system and reconstruct the results, and that's kind of a pain. And you also have to deal with the management headache of managing the shards themselves. What do you do when they go down? It's a significant availability concern. Now, a significant or another option is a shared nothing architecture. Now, with a shared nothing architecture, you're connecting things at the SQL level, and this can also work pretty well, like sharding, but you do have a risk of a higher failure rate if you scale out too far. With a shared nothing system, if each node basically owns its own subset of the data, and if a node goes down, you've lost access to that data, so the higher failure rate is a significant availability risk in this case as well. By the way, I do see a lot of questions coming in. Our moderators we're going to do our best to keep up with them as they come in, but we will also be taking time at the end to try and address any that we may have missed. So please keep them coming. So in addition to shared nothing, another option is shared disk. So with shared disk, the system like Oracle RAC, you essentially fuse the caches together, and you have a common storage layer that all the nodes have access to. So, this has the advantage that you can actually lose nodes without losing data. All your nodes have access to all the data, which also makes it easier to do something like load balancing. Now, the problems with this system, there are issues with hotkeys that you can run into. There are distributed locking issues when you have all these nodes accessing the same storage. So again, you run into availability issues when you're trying to scale the system up really high. Now, of all the options I just showed you, one thing to notice is that the blue box, that collection of functionality, the SQL transactions, caching, and logging were basically the same in every option. We were just taking that thing, sticking on a box, and maybe we try and replicate it, and we try to do clever things at the storage layer, but that section wasn't changing. And that's something that we viewed as a problem that needed to be solved when we were designing Aurora. I mean, it's a problem, in our opinion, for cost, flexibility, and availability. So on the cost side, when you're having to buy bigger boxes and these bundles of boxes, the bundles of functionality, it's not as efficient as a scale-out system. It can be very expensive. On the flexibility side, having everything on a single box, it leads to inefficiencies because you're buying a bundle of resources when you may only want more of one of them. Like, let's say you want more cache resources. That can, if you're using up all of your resources currently, your choices are basically to buy a bigger box or buy more boxes. So maybe you're buying more cores or basically resources you don't need. So it's less flexible and less efficient. And we spent some time earlier talking about how these options can basically lead to a bit of an availability hit, which is not desirable. So if you were in our situation, you're trying to reimagine the relational database, and we're in a different era now. It's not the 70s anymore. Like, how would we construct a relational database if we were redesigning it more in the cloud era? And the things that we thought about were, we certainly wanted to maintain the advantages of a relational database management system. You want SQL. You want the ability to say, look, here's what I'm trying to do. You figure out how it's going to get done. I don't want to deal with that. You want transactions, which is essentially saying I don't want to have to deal with concurrency. I want my database to commit a transaction and just have it work. And at the application level, I don't have to worry about it. You wouldn't want the big box approach that we were talking about earlier. You would want more of a scale-out system that had better cost and flexibility. You would also want to leverage what certainly wasn't available in the 70s, which was modern cloud services. You would want some of the more robust services that AWS offers that can give you higher availability, but also the ability to have self-healing resources that can recover from failures on their own. So our goal, we took all of those desires, and the goals that we came up with are what are shown on this slide. We wanted to create a database that was, it gave you the speed and availability of a really high-end commercial database, but not the costs, in particular the licensing costs that tend to come with that. We wanted something that was, as simple and cost-effective as, an open-source database like MySQL, but we also wanted drop-in compatibility with MySQL. We didn't want you to have to work too hard to try this out. If you had to move to more proprietary APIs just to even try the service, that's a hurdle that is painful for developers. So Aurora is designed to be compatible with MySQL 5.6 and higher. We wanted simple pay-as-you-go pricing, which again is something that we strive for in most of our AWS cloud services. We didn't want you to have to buy a big box. We wanted you to be able to scale your resources as needed and dial them down as needed. And we wanted all of this to be delivered as a managed service. So this led us to what we refer to as a service-oriented architecture. And one of the first things we did was we moved the storage and the logging layer to a separate scale-out fleet. So this is the first element of that blue box that we were talking about earlier that has been, for the first time moved out of the blue box. So the logging and the storage layer are actually a separate multi-tenant fleet that scales independently of the database instance itself. The other thing we did is that we built Aurora on top of modern cloud services. So on the control plane, for example, is integrated with services like Amazon DynamoDB, Simple Workflow, Route 53, and other services. And on the data plane, we have continuous backups to S3, which is designed for 11.9 of availability. So pricing. So with Amazon Aurora, there are no license fees, and there's no lock-in. We don't, we are fully MySQL compatible. We don't, it's easy to move your applications onto Aurora or off of Aurora. Now, the per instance fees are roughly 20% higher than the equivalent instance on, say, RDS MySQL. However, we do expect a lot of our customers to actually save money by migrating from MySQL to Aurora, and there are a couple of reasons for that. One reason is that our storage layer is actually pay-as-you-go and auto-scaling. So all Aurora databases start at 10 gigabytes, and as you grow the database by adding more data into it, the storage layer will actually automatically grow and provision more resources for you as you need it. So, for example, if you were planning for a database that would grow from nothing to 64 terabytes over the course of a few months, you wouldn't need to provision 64 terabytes in storage volumes and pay for that while you wait to actually use it. You would pay only for the amount of data that you've put in, and Aurora would just scale it up to handle it for you. So our own analysis of customer data shows that a lot of our customers have tended to over-provision on storage over the years, so we expect customers to save quite a bit of money by switching to a pay-as-you-go storage model. So that's one way that we think they'll save money. Another one is performance, which is something we'll talk a bit about later in the presentation. Aurora performance is really strong, particularly compared to MySQL. And we think that customers will be able to save money by actually moving to smaller instances than they were on MySQL. Or if they were, if they had, say, a sharded strategy, or they had a MySQL cluster, they could actually reduce the number of instances they need to support their application. So we talked about drop-in compatibility with MySQL. So we wanted it to be very easy for you to migrate your application to Amazon Aurora from MySQL. But that doesn't just mean your application, that also means the ecosystem surrounding MySQL. And it should just work. We have a number of partners listed here, and there are more offline, where they've actually certified their tools that are designed to work with databases like MySQL or MariaDB, and they've certified that they actually work with Aurora. And certainly if you have a tool that's working well with MySQL 5.6 and higher, and for any reason doesn't work with Aurora, we certainly want to hear about it. Please let us know. Please come to our forums and let us know, and we'll fix that immediately. Now the actual migration process to Aurora is relatively easy. I mean, we go into more details in our documentation, but the two-step process is you establish a baseline, you do a standard MySQL dump and import, and then you can take a MySQL snapshot and import it directly into Aurora. You can then take, use binlog replication to catch up on any changes that you may have missed while you were doing that. Now, to actually take that first step is quite easy if you're an RDS MySQL customer already. So this is a screenshot of the RDS MySQL console. So if you have a MySQL database already in RDS, you just click on Instance Actions and then go down to Migrate Database, and there will be a very short wizard that will guide you towards setting up a copy of your database in Aurora. Now, we also talked about Aurora being easy to use. And part of how we achieve that is that Aurora is part of the Amazon RDS family. And so actually, if any of you were trying to start an Aurora instance and having trouble finding it in the console, the way you get there is you actually go to the Amazon RDS console, and you go to the instance creation wizard, and then you choose Aurora as the engine that you want to build on. So as part of Amazon RDS, or Relational Database Service, we get a bunch of simple database management benefits. RDS gives you the ability to create a database in minutes. It gives you automated patching, push-button scale, which is you could take an instance and scale up to a larger instance as your needs require. And you have continuous backups to S3 and automatic failure detection and failover. So a lot of benefits that come with being a part of the RDS family. We've also taken steps to simplify the storage management layer. So read replicas are available as failover targets with no data loss. And we'll talk about that a little bit later, but effectively the read replicas have access to the same scale-out storage layer that the master does, and so you can immediately fail over to a replica without having to basically replay all of the logs. It immediately has access to the data. You can instantly create user snapshots without a performance impact. We have continuous incremental backups to Amazon S3. And automatic storage scaling up to 64 terabytes. And scaling storage, has always been an availability concern in the database world. You always have to worry that you're approaching a limit, and then you have to re-provision and deal with all the headache of that. This is something that Aurora will handle for you. It will detect that you're approaching, however much data, space that you've provisioned, and then we'll automatically scale it up for you without requiring any input from you. Now, you can put a cap on that if you want to. This is not an unbounded database if you don't want it to be. You can specify that the volume is limited to some amount, but we give you the ability to auto-scale. Now, we've also claimed that Aurora is highly available service, but we need to explain why, so you don't just take our word for it. And part of that is that we've made some pretty nice innovations on the Aurora storage layer. So on the storage side, all of your storage is broken up into 10 gigabyte chunks, and each chunk is 6-way replicated across 3 availability zones, or AZs. And if there's any issue on a single replica or a single node, Amazon Aurora will automatically recover. It'll either repair or replace the node that is having issues. Now, Aurora has 4 of 6 write quorum, which means that we will acknowledge a write as successful once it's been successfully committed on at least 4 of the 6 replicas. This does mean that you can lose 2 nodes in Aurora out of 6 without having any impact on the write or the read transaction rate that we can support. We also talked a bit about scale-out multi-tenant storage, which again automatically scales as you need more and goes up to a pretty hefty 64 terabytes. The other thing we've done is we've decided to use a log-structured storage system. So we have many small segments that are replicated across AZs, as mentioned. The log-structured storage, it also gives us the ability to eliminate chatter between the database level and the storage level. This more efficient setup means that more resources are available on the read replicas for actually handling reads as opposed to just keeping up with the master, which is very useful because that's what you wanted your read replica for in the first place. And Aurora is self-healing and fault-tolerant. So, as I mentioned earlier, you could lose 2 copies, or effectively an entire availability zone could go down. It wouldn't have any impact on the read or write availability of your database. You could lose 3 copies and still have the ability to read at the same level as before. And of course, if any partition or node goes down, it's Amazon Aurora's responsibility to detect, replicate, and correct the replication. Now, we've also talked about or hinted at very fast crash recovery, and we're actually going to claim instant crash recovery, which is a pretty bold claim that we really need to back up. So here we go. With a traditional database, you would tend to checkpoint your logs every 5 minutes, and the idea there is to ensure that you only have a fairly limited amount of logs that you would need to replay in the event of a failure. So that's good, but so let's say you were trying to do a recovery in the case of a MySQL master node failure. Recovery in MySQL is likely to be single-threaded. You could have a massively parallel app that's writing to your database for 5 minutes and then trying to recover with a single-threaded process, which can create a bottleneck. In our experience, we've seen it take tens of minutes and in some extreme cases even hours to recover the 5 minutes of logs in a failure scenario. So with Aurora, you can replay redo logs on demand, and this is partly just due to the nature of the log-structured storage. You write to Aurora and you read later, and the logs can catch up if needed. When a data page is being read, the storage system can determine if the page is actually caught up. If so, it returns a result. If not, it replays the logs and returns when it's available. So there are 3 distinct advantages that Aurora has in this scenario. One is that the replay of the logs can be done in parallel. It's not limited to a single-threaded operation. A second advantage is that it's distributed and that it can take place across a number of machines. And a third particularly important advantage is that replay of logs in Amazon Aurora is asynchronous. And what we mean by that is that you don't actually have to wait for that process to finish before you can start using the database. You can start accessing the database, and if that section of the database, if the replay is complete, you'll get the data back that you need. So the storage layer is part of why we can recover from disaster scenarios very quickly. But another one is that we have survivable caches. So again, this is something we've tried to move out of the sort of monolithic architecture. We've actually taken the caching out of the normal database process. What this means is that if you need to restart your database, if you have a failure on your master node or on a replica, the cache is actually still warm. It's still, it persists beyond the lifetime of the database, and when when the database comes back up, the cache is still there. This is very important, I've run into this. I bet a bunch of you guys have run into this. I mean, there can be a scenario where you go through all this trouble to recover your database under emergency conditions. You bring it back up, and you realize the cache isn't warm, and the performance of the database, even though it's back up, is really not where it needs to be until the cache warming is complete. And there are cases where the cache warming can actually take longer than the recovery of the database itself. It's a very stressful and painful experience to go through. With Aurora, the cache stays warm, and so that really helps bound the limits of the cache recovery process. Another advantage is that Aurora replicas can actually be promoted instantly. And the reason for that is that since we've taken the storage layer out of the database, there's actually a shared storage layer that both the master and the replica can access. So with MySQL, the replicas would be logical replicas, meaning that you would send an update to the master, and the master would send that query onto the replicas. And the replicas would have their own copies of the data, their own storage, and they would apply the change to their storage, and that's how the update would happen. So this works, but it has some disadvantages. I mean, you have a single read replica, you've already doubled your storage costs, potentially more, and so that can be expensive. The replication is typically single-threaded, which means that you can have an expanding lag where the replica, the data that's available on the replica is falling behind the data that's available in the master. And depending on the application, that lag can actually grow almost indefinitely. The third concern is that lag can lead to data loss in the event of a disaster. So if the replica is behind and the master goes down, the replica may not be able to, there may be a gap where there's just some data that was written to the master that the replica will not have access to. So by contrast, since Aurora replicas actually access the same storage system as the master, you don't have that same risk of data loss. So if the master has acknowledged an update operation, so it's committed, it says, yes, I've got the data, that means it's on disk in the shared multi-AZ storage layer that the Aurora replica is also accessing. So even if the master goes down, the instant it commits the write, the Aurora replica has still got it. The Aurora replica also has a very tight bound on replica lag. We typically see, about 10 milliseconds, often less. I'll show you some numbers later that show it's fairly consistently less than that. Now I mentioned that we're MySQL compatible, and we've tried to stay very, very close to MySQL, nearly identical to ensure that we don't introduce something that's specific to Aurora. But this is the one case where we deliberately chose to break that rule, in that we've added some features to Aurora that actually let you simulate failures. So we've talked about Aurora being a highly available system, a fault-tolerant system that can repair itself. But we also build our systems to fail very rarely. So that's a hard thing for customers to test. So we've actually given you a way to do that. So with a simple SQL command, you can actually do something like create a crash failure on a database node, simulate disk failure, networking failure. You could take down a read replica or degrade the performance of the read replica and so on. So this lets you test our claim. Now I encourage you to try it. Just go beat on Aurora a little bit and see how it performs. This also helps you build highly available applications around Aurora because you can test how your system, how your entire application will behave in the presence of a failure on the Aurora side. Now, I've made the claim that Aurora is fast, and at this point that's a marketing claim because I haven't given you any numbers. So let's talk about some numbers. So here are the results of a SysBench benchmarking exercise we went through. So SysBench, if you're not familiar with it, is a benchmarking suite that's pretty standard for MySQL testing. We ran this on an R3.8XL, which is a pretty beefy machine with 32 cores and about 244 gigabytes of RAM. We ran this with 4,000 threads. So that's 4 clients, each running 1,000 threads. And by the way, a pretty good performance tip for Aurora, versus other engines, we see the best results with higher concurrency workloads. So if you're running a benchmarking exercise, I strongly recommend higher concurrency workloads. So in this case, on an R3.8XL machine, we're getting about 105,000 updates per second. And our average latency is 0.276 milliseconds. So this is an update workload, so we're doing writes, and the average latency is less than 1/3 of a millisecond in this case. Here are some read numbers. So again, we're doing MySQL sysbench. We're doing a select-only workload. So this is a relatively simple workload. We're basically probing for individual records from a single table, so we're not doing joins or anything like that. So relatively simple gets. And so this machine is the same as in the same setup as in the last benchmarking exercise, same machine anyway, although a single client with 1,000 threads in this case. It was able to achieve about 546,000 requests per second. So we're over 500,000 requests per second. And the latency is down at 0.054 milliseconds on average. So to put that in context, that's less than an 1/18 of a millisecond average latency. Now we talked a bit about read replica lag before. So here's some actual numbers on that. So in this case, we're running just under 14,000 updates per second. And our replica lag is coming in at just about a little under 7.3 milliseconds, which is pretty good. I mean, that most applications will have a tough time actually being affected by that. Now, we also tried this. We don't have the same all the same numbers on it, but we ran this test on MySQL on the same hardware, and we found that gave us about 2 seconds of lag, and was only able to achieve about 2,000 updates per second. So, with this setup, we found that Aurora's lag was about 275 times faster, or so the lag was 275 times smaller than what we were able to achieve on MySQL, while achieving a throughput rate that was about 7 times higher. Another test we ran was looking at how the performance of the database would vary as the number of tables went up. So if you look at the 3 columns on the right, we tried 3 different setups for MySQL, 2 on EC2 and 1 on RDS. And we varied the number of tables from 10 up through 100, 1,000, and 10,000. And this was a workload running with 1,000 connections. So what you see is that you get in 2 of the 3 cases you get some performance improvement as the number of tables goes from 10 to 100. But as you get up to a larger number of tables, you actually get some pretty significant degradation. So down at 10 tables, MySQL is achieving in the neighborhood of 18,000 to 25,000 operations per second. And once we got up to 10,000 tables, it had dropped pretty significantly to about 4,000 to 8,000 operations per second. Now on the Aurora side, Aurora was not immune to this effect, but it was much more stable. So we started off at about 60,000 operations per second, which is a little better than double what we were getting on MySQL. And as we got up to 10,000, it did degrade by about 10%, so down to 54,000 operations per second, but much more stable and maintaining the same order of magnitude. We also tested at higher concurrency, and here, the reason you would generally apply higher concurrency is that you would want to see a significant improvement in the performance of your database. That's why you do it. So we took the number of connections up from 50 to 500 all the way up to 5,000, and on Aurora we saw, or on MySQL we saw, a very significant improvement going from 50 to 500 threads. But as we got up into the 5,000 range, we started to see fairly significant degradation. On the Aurora side, we did see the throughput that the table was able to achieve continue to grow even all the way up to 5,000. We also did a comparison on the replica lag that we saw with Aurora versus MySQL. So here we took the scale from up by an order of magnitude. We started at 1,000 updates per second, and we took it all the way up to about 10,000. So MySQL started off just fine, down at the 1,000 level, and we did see pretty significant increase in replica lag as we took our experiment up to the 10,000 updates per second range. Here again, Aurora was not immune to the effect. But the impact was much more contained and remained much closer to where it started, with Aurora starting off at about 2 milliseconds and ending up at 2.6 and ending up at about 5.4. So up by a couple of milliseconds, but really maintaining a fairly consistent performance. And 5 milliseconds replica lag is you might call that near synchronous. It's not actually synchronous, but most applications are not going to be that sensitive to a few milliseconds of drift between the replica and the master. At 60 seconds or 300 seconds, that's where you certainly start to notice that. So the numbers that you've shown give you some insight into how we've been thinking about Aurora. We wanted a database that would perform very well, would grow with you, and continue to perform well as your application got bigger. We didn't want to see a massive change in the nature and the performance of the database as the scale changed. We wanted to grow with you and continue to serve you as well as we had when you started. And we're going to go to questions shortly and also talk a bit about the survey, but the 2 links I did want to call out. So the top one is the Aurora website. It's aws.amazon.com/rds/Aurora. Where you can find a lot of the information that I've shared with you, and it's a good starting point for learning more about Aurora. The second link is particularly useful. It's /RDS/Aurora/getting started. We've got a lot of really useful resources there. We have a guide showing you how to connect to Aurora. We have some information on benchmarking. We have links to our documentation and other useful getting started guides. So I strongly encourage that you check that page out.